gases a little bit. And we're going to talk about reversible work. So reversible work, I can go to the first law and I can write out the first law. Right. Incremental change in reversible work is equal to the change in internal energy in my system minus the incremental amount of work done on the system, right? So work reversible, work done on system. Okay. So reversible work, I can have a steady flow problem. So I have mass coming in and mass leaving, and my turbine is let's say doing reversible work output. Okay. Mass in, mass out, remove some of the internal energy from my gas in, and that amount of energy I remove from my gas in relative to what's is providing work. If I make it reversible, completely reversible, right, I have no heat loss, right? No irreversible heat. Okay, so in this type of, I can write work reversible related to flow. Right, this is a steady flow problem. Flow in, flow out. This is equal to the integral from 1 to 2 V dP. I could use a small w, work reversible for flow is equal to the integral from 1 to 2 small v dP. Okay, I'm going to get back to this in a second, this expression, because we haven't talked about this type of work before. We've really talked about boundary work, but let's go to something where we know it's boundary work. So now I have a closed system, I have my engine, and I have work reversible associated with the change in the volume, right, and pressure of my system. I have boundary work. So if this is my initial volume and it expands, my engine does work on the surroundings, right? If I compress it, then the surroundings do work on my engine, right? So closed system, moving boundary work. Work reversible let's call it boundary, let's say, I could say control volume, but let's just not for flow, I'll say moving boundary. Okay, work reversible moving boundary is equal to minus the integral from 1 to 2 P dV. I can make this a small w, work reversible, so this is the work per unit mass. Moving boundary is equal to the integral minus 1, 2 P d small v. So related to this, I can write out my TDS relation. TDS is equal to du plus P dV. This is the first TDS relation. With this one, I have this VDP. I have TDS equals DH minus VDP. Okay, so minus dPV, right? let's integrate both sides. Integrate this side. Integrate in here, I got delta H. Integrate here, I got that. Right? One represents, I want to move this down a little bit so I can illustrate this a little. I can reach, I'm not giant. So this is my control volume of mass entering. Okay? Comes in hot, I'll grab a red top. So, comes in red, say hot, lot of energy. Leaves going out like this, okay? The change in enthalpy is related to the work output, right? When I do this, I have this term here. So I can draw a boundary around this, right? And do first and second law analysis. Energy balance and entropy balance on it, right? So this is kind of a TDS relation, but it's related to entropy balance. So I have a boundary around this, and I have a control volume of fluid passing into my system. Then I have a control volume of fluid leaving my system, right? This work, so let's just look at what it does in time, okay? My control volume. So before we've only talked about the moving boundary work, which is easy to picture. This is center of mass moving control volume work. Now, say this thing was expanding, okay? This control volume. So it comes in this big and it leaves as big as my hand. This control volume would be doing boundary work, right? Because it would be expanding. But in this formalism, we're not discussing it that way. So this part right here is the moving center of mass kind of flow work. So, or translational work. So just like you have a block on an incline, right? Say just you have a square, physics 1, right? Freshman physics. You take a block and you want to move it up some ramp. That required a force, right? To move it up. Well, we calculated the amount of force you can need to move it up a ramp at such height. That's just related to its displacement relative to a distance times, so it's mass times gravity times the height it displaced, right? That was a force, but I had a block. So I look and I have a surface area on that block. So a force divided by a surface area is a pressure. Here, I have a control volume. There's a pressure here. It might have high energy, right? Because it's hot, so let's go back to my red one. But I have a pressure here. And it comes out here if there's a pressure here. This is kind of like a force, kind of the moving block, but now I'm dealing with the fluid. So, flow work. Moving center of mass of a control volume. Translation, right? Block up. This one, fixed in space, just expanding. Boundary work. So I can have a moving translational work, flow work here, and then, so the second TDS deals with translational work, and the first TDS deals with boundary work. More for an engine, more for pumps, turbines, things like this, where you actually have fluid flowing through your system. Okay, so now that I did all this, I have steady flow. Let's stick with the steady flow one. And I'll just write here, second TDS. Let's put a label on this. Now, I've never really heard anybody really define this before, but it just realized to me that I've been wanting to do it. I finally came up with a good analogy with the ramp. and the pressure and force from freshman physics. So what should we call it? Because I haven't called it anything in any other notes before. I don't remember ever reading a specific name for this either. So what should we call it?
Getting a workflow per mass. Just call it the popular word.
No, it's not that. It's defined somewhere. I never recall it. This is I've seen so many times boundary work, right? Very, very easy to visualize. This deals with two control volumes and one coming in and leaving and a pressure. And so translational control volume work, I don't know. Translational boundary work. So I don't know. So this was moving boundary, so I should have changed that. So I'll just say I'll call it translational VP work, and then this one moving boundary PV work. So I've already used that, moving boundary PV work many times. So translational or translation boundary VP work. I don't know. I'll have to come up with a better name. Okay, so let's go back to the reversible work. So we have steady flow, reversible work. I still have the same first law expression, equals du minus integral work reversible flow. I can make it small q, make it small u, make it small w. But now I'm doing flow. I could do boundary. This expression just changed whether I flow or boundary. It still worked. But given I have flow, and I also know from my second TDS relationship, right? What is this equal to? TDS. It's equal to that. But I can't really just do only that. I have plus d kinetic energy plus d potential energy. So this is my 8, this is my u, right? Minus delta work reversible flow. So I have delta Q reversible. I'm going to add this to both sides. Plus delta work reversible flow is equal to dH plus d my kinetic energy plus d my potential energy. I just said this earlier, Q reversible is equal to T ds, and I know that T ds is equal to dH minus V dP. So my delta, okay, so now that I have this, let's explain what I'm going to do here. So I have this piece here, right, which is coupled, right? This and that, I have my TDS relationship, I replace that with, that's what I get. and I have my Q reversible. So I take this and I go dH minus V dP. Right? Using that piece. Plus my work, incremental work reversible for flow, equals dH plus d, my kinetic energy part, plus d, my potential energy part. So my work, if I integrate both sides, reversible flow, and I subtract that over to there, let's just write it. It's not integrated yet. So I'm just going to take this part, bring it over here. So work reversible flow is equal to V dP. There's not one over here. My H's cancel out. Plus D kinetic energy part plus D potential energy part. Or I can write it as work reversible for flow and just integrate both sides equals the integral from 1 to 2 V dP. And now because I integrated both sides, this just ends up being a delta kinetic energy and a big delta potential energy. Now the question is, for a steady flow problem, let's try to stay like that. For a steady flow problem, and I have, what is the change in kinetic energy from here to here? 0. So for most turbines, they're not the size of, they're not 100 meters big, right? So my potential energy, or if I look at it, if I was going to say reversible work associated with a pump, right? Usually there's very small pressure difference due to sea level. So this term for steady flow is 0 for sure. This term is approximately equal to 0. So delta kinetic energy equals 0, delta potential energy equals approximately 0, which then gives me work reversible for flow is equal to the integral of V dP 1, 2. So anyways, I already told you it was like that earlier, and basically I just derived it, right? So this is the work associated with translating a control volume, right? In a process, through a process, or through a system. Control volume of fluid. For a turbine, so I'm going to make this less than or equal to or greater than or equal to, and I want you guys to tell me which one it should be. So, turbines do what? Generate power, work per unit time, right? So for a turbine, what should this be? Greater than equal to 0 or less than equal to 0? Less than equal to 0? Okay, I was thinking the other way around, but you're right. For some reason. Yeah. Now I got confused because I was starting to think the other way. But anyways, if I go back up, so that is work reversible output, but that's not that part there, what I show for the turbine doing work, is not because of that PVDP. That's the flow part. That part there deals with changing the enthalpy of my fluid, right? So basically changing its temperature and pressure. The flow part is here. This is work done on or by the turbine. Yes. So the work done on the turbine is here. The turbine does work, right? So the work done on the turbine is this. Work done by the turbine is positive. So if I consider a pump, so this, I'm going to circle this in red, and I'm just going to say energy producing device. Okay, for a pump, and or compressor, I have my work. So turbines still have fluids flowing through them, right? Pumps and compressors also have fluids flowing through them. So my work reversible flow is greater than or equal to 0. So work done on a pump / compressor is positive. Work done by pump / compressor is negative. And in this case, I'll circle it blue. And I'll just put an arrow . So energy consuming device, you increase the reversible work, flow work, right? So let's just think about this. If this is reversible, how does this compare, the reversible flow work for a pump compared to the actual? So, okay, it's greater than or equal to 0. We know this is a positive value, right? We increase the energy of our fluid from a pump or compressor, right? We get flow going. So this part is positive. The pump's consuming, or the compressor is consuming energy to do reversible flow work, or work for flow to get the fluid moving. And this is the reversible part, so this is the ideal, no heat loss, right? But how would this number here compare to the actual?
Would that be higher than the actual?
I consume a certain amount of energy to get this, to get flow.
You're going to consume more energy in actuality.
So is it less than or greater than?
Greater than.
This is greater than that?
Yes.
The actual is less than the work.
Do Well, actually, yeah, it is. It's like that. Because the other way is the other way around. So you had it right. So the reversible work that you have, I shouldn't put reversible. I should put flow actual. Now for a compressor or for a turbine, I have, well, it was right the first time. Anyways, it's getting messy. Fix it later. And we'll go here. I just want to summarize this because I'm running out of time. So I have work done on the system, internally reversible. I could do this for flow, right? Work done by the system, right? So I can do on the system. For flow, on the system this was positive. I had that. If I want to turn it to work by the system, I have to multiply everything by a minus sign. So this is work in. Now, if I say by the system, that's work out. So I can always do things like this: work in, work out, negative work out. Okay. So special case, no work done at constant. So my reversible work flow is equal to 0. And then I have all of this. And this is the Bernoulli equation in fluid dynamics. So let's go back to our reversible versus actual. So I can define my reversible amount of heat. So dH plus kinetic plus potential minus my reversible part, right? So this is work done on the system. Here I have actual, so dH, this is a D, kinetic plus potential, and then I have, since this is actual, I have my actual amount of work, right? So if I subtract my reversible from my actual, I get minus reversible plus work actual. And I know this is true look at my TS diagram, and I look at a reversible process, so I go from 1 to 2 and back. My reversible, this has to be equal to 0, right? No area. And my actual is larger, okay? Actual. So counterclockwise out, this is work, the actual heat is out. Okay. So my reversible is 0 minus a positive number, right? So I can compare my reversible work with my actual work. So so let's leave this over here and let's bring it just over. So I have, I'm integrating so I know to go through this process, right? So I have Q actual which is a positive number. I've identified it right there. This, when I integrate it, right, so I can integrate both sides, right? So I get that. And then I have I integrate that, so I have plus work reversible equals work actual. So in this case, because I know that is there, work actual is always going to be what? Larger, greater than, or less than work reversible. So let's just say my actual heat loss was 0. Zero area. Then they would be equal. So work actual less than equal work reversible. Now remember, the directionality of this, whether it's clockwise or counterclockwise, is dependent upon, right, whether it's an energy consuming or energy producing device. So just as a rule of thumb, right, this goes counterclockwise. If you remember an engine, it was clockwise. No, actually, engine was counterclockwise, the other way was. So this one here, so this is an engine energy producing device. Energy producing device, work actual is always less than or equal to work reversible, which makes sense, right? So the end story is that. Energy consuming device, the amount of energy you have to put in is always going to be greater than the amount of energy ideal. Energy producing device, the amount of energy you get out is always going to be less than the ideal case of energy out.